Now, this is quite a story from NASA because for the second time in history, a man-made object has left our solar system. NASA has confirmed that the Voyager 2 probe is now in interstellar space after exiting the sun's protective bubble, which is called the heliosphere. Voyager 2, the Intrepid spacecraft launched in 1977, has once again defied expectations and expanded our understanding of space science. After decades in space, having traveled more than 12 billion miles from Earth, it recently transmitted data from a region far beyond the known planets, a place where sunlight is but a whisper, and the rules of space seem almost rewritten. The discovery it made at the edge of the solar system was nothing short of remarkable. Voyager 2 encountered a region of space where the behavior of particles, magnetic fields, and plasma flows differed significantly from scientists' predictions. This wasn't just a surprising twist, it was an unexpected one based on our current understanding of physics. Before we start, please like and subscribe for more updates. As Voyager 2 drifted further into interstellar space beyond the heliopause, the boundary where the sun's influence fades into the interstellar medium, it began detecting unusual anomalies. Sensors built to measure charged particles, cosmic rays, and magnetic fields began transmitting data that didn't align with expectations. Cosmic rays, which were expected to be relatively evenly distributed, instead surged in unexpected patterns, fluctuating in irregular intervals. The magnetic field, rather than weakening and diffusing as anticipated, showed unexpected characteristics. Even more intriguing, high-energy particles appeared to interact with Voyager 2 in ways suggesting an unseen influence in space. This deviation from the norm wasn't just a hiccup in the data, it persisted, patterned, and consistent, demanding serious attention. The idea that a spacecraft could cross the heliopause and find a distinct magnetic field challenged established models. Voyager 2's onboard magnetometer recorded a change in field strength that simulations had not fully predicted. The intensity of the magnetic field differed from what Voyager 1 had observed when it crossed into interstellar space years earlier, and the direction of the field was distinct, suggesting that the two probes might be encountering different interstellar environments despite their relative proximity in cosmic terms. At first, some scientists suspected an instrumentation error. Voyager 2 is over 45 years old, after all, operating on an aging radioisotope thermoelectric generator and designed with 1970s-era electronics. But multiple checks confirmed that the instruments were functioning as intended. The signals were real, and they described a phenomenon that expands our understanding of heliophysics. The findings were significant. What Voyager 2 was seeing was unexpected. One of the most notable findings was the behavior of the plasma that drifts through this remote boundary. Plasma, the hot, ionized gas that comprises much of the universe, was expected to be sparse and sluggish in this region. Instead, Voyager 2 found it to be denser and colder than anticipated, suggesting a transition zone between the heliosphere and the true interstellar medium. This plasma didn't behave like the solar wind, nor did it fully match interstellar plasma. It was a unique state that had not been observed before. This unexpected zone, denser than the solar wind, and yet too cold to be driven by the sun, raised immediate questions. Could there be an interstellar layer surrounding the solar system? A previously undetected region separating us from the broader galaxy? Adding to the mystery was the way radio waves propagated through this region. Voyager 2 had been periodically pinging signals back to Earth, and these transmissions showed subtle variations. Scientists analyzing these radio signals discovered frequency shifts and phase modulations that suggested complex structures in the plasma, possibly indicating dynamic interactions. These weren't the kind of variations one would expect from a simple, homogeneous cloud of interstellar material. They pointed toward a complex, possibly layered structure at the edge of the solar system. If such a structure exists, it suggests the heliopause is an active frontier with unique properties. Magnetic reconnection events, where magnetic fields snap and realign, were another notable feature of this boundary region. Voyager 2 detected rapid changes in magnetic polarity, events that released bursts of energy previously thought unlikely so far from any stellar body. These magnetic anomalies resembled processes observed near stars and black holes, occurring in what was assumed to be relatively calm space. The implications were significant. If the edge of the solar system can host such events, it might be more dynamic than previously thought, driven not only by the sun, but also by interactions with the galactic environment. But perhaps the most puzzling piece was the unexpected variation in cosmic ray distribution. Voyager 2's cosmic ray detector observed an asymmetry. More high-energy particles were arriving from one direction than others. These weren't solar particles. They were galactic, possibly extragalactic, yet their distribution suggested an influence shaping their approach. This directional bias was not fully anticipated by existing models of interstellar space. It hinted that something out there, possibly a magnetic or gravitational feature, was affecting the trajectory of these high-energy particles. If such a mechanism exists, it could suggest the solar system interacts with undetected structures in the interstellar medium. This possibility led to scientifically grounded speculation. Could the sun's movement through the Milky Way be influencing the interstellar medium, creating a dynamic region? Alternatively, perhaps the galaxy has magnetic structures that Voyager 2 is encountering. The idea that there are magnetic features in interstellar space stable enough to influence plasma and particles at such distances challenges our understanding of the interstellar medium. Not only are these findings significant in a theoretical sense, they also prompt a reevaluation of the solar system's relationship to the galaxy at large. For decades, scientists have treated the heliopause as a loosely defined edge, marking the transition from solar to galactic influence. But what Voyager 2 is revealing is more complex and dynamic. The boundary may act less like a fence and more like a membrane, semi-permeable, reactive, and variable over time. If the heliopause can change significantly, it raises an intriguing possibility. The solar system is an active participant in a larger galactic ecosystem. One of the more intriguing implications centers around the possibility that these structures could influence cosmic radiation reaching the inner planets. If the outer boundary of the solar system can affect cosmic rays, it might act as a kind of cosmic shield. But this shield is not constant. As the solar system moves through the galaxy, encountering clouds of gas or magnetic fields, this boundary could shift, potentially altering radiation levels on Earth and its neighbors. This might have implications for climate or biological evolution over geological timescales. In other words, what Voyager 2 has found could be key to understanding how galactic scale forces influence Earth. Even more intriguing, there's the suggestion that what Voyager 2 is encountering might be a previously undetected state of plasma. The idea of a unique plasma state, neither fully solar nor interstellar, is novel. It might represent a transitory phase that only exists in boundary regions, opening new questions about cosmic matter. The fact that such a discovery was made by a decades-old probe using 20th century technology deepens the sense of wonder and curiosity. And then there's the speculative idea that we might be witnessing phenomena that challenge conventional explanations. While still within the realm of scientific inquiry, some researchers have considered whether the unusual structures Voyager 2 is sensing could be linked to complex astrophysical processes, perhaps influenced by large-scale galactic features. Such a notion remains unproven, but its discussion highlights how Voyager 2's findings push the boundaries of scientific thought. What Voyager 2 has stumbled upon may be seen as one of the most important scientific revelations of the 21st century, not because it gave clear answers, but because it raised new questions. The unexpected nature of its findings, denser plasma, distinct magnetic fields, asymmetric cosmic rays, and altered radio signals indicates that we've only just begun to grasp the architecture of our galactic neighborhood. Every new bit of data from that aging spacecraft brings the promise of more insights, more challenges to our models, and more reasons to remain curious. Voyager 2's discovery has shifted our cosmic perspective. It reminds us that even after centuries of charting the heavens, we remain at the beginning of understanding the universe. The edge of the solar system, once thought to be a quiet horizon, now stands revealed as a dynamic, unpredictable realm filled with forces we are only beginning to comprehend. With every signal Voyager 2 sends home, humanity is prompted to rethink its place not just in the solar system, but in the galaxy beyond. In that small window between the known and the unknown, wonder thrives. Voyager 2's detection of this uncharted region at the solar boundary has not only challenged long-standing assumptions about space physics, but also initiated a new domain of inquiry. With this development, researchers are now faced with data that doesn't fully match established models. The flow of particles, pressure gradients, waveforms of energetic electrons, and interaction patterns among magnetic fields are behaving in unexpected ways. This complexity suggests that the heliopause isn't simply a passive border, but a transformative zone, where solar origin material undergoes transitions as it becomes part of the interstellar environment. Among the most fascinating elements emerging from Voyager 2's recent transmissions is a discovery involving wave-particle interactions observed in this region. These are interactions where particles interact with magnetic or electric field waves, causing them to accelerate or decelerate. Previously, Such interactions were thought to occur primarily near strong gravitational or electromagnetic sources like stars or compact objects. But Voyager 2's instruments captured a new kind of wave-particle resonance, one that appears to transfer energy between particle populations without typical thermal signals. This might be a mechanism unique to the hybrid zone it is exploring, where solar and galactic forces interact. Moreover, this phenomenon points to the presence of organizing forces. For waves to propagate in this manner and transfer energy without losing coherence over vast distances implies the existence of stable structures. These might be filamentary magnetic fields or large-scale electric field configurations sustained by galactic currents, possibly remnants of ancient shock waves or supernova remnants absorbed into the interstellar medium. The presence of such coherent features in a supposedly chaotic part of space is both perplexing and exciting. The spacecraft has also detected what appear to be temporal oscillations in the density of interstellar particles, cyclic changes that suggest a pulsing pattern in the interstellar medium. These pulsations don't seem to align with solar activity or known galactic phenomena. Their periodicity suggests a source of regular influence that could be operating at scales previously unaccounted for. Some theories propose that this might be evidence of the solar system moving through a structured wave of interstellar gas, possibly caused by gravitational perturbations. Further complicating the picture is a form of spatial anisotropy, subtle, directional differences in the behavior of magnetic fields and particle flows. Rather than a uniform gradient from the Sun outward, Voyager 2 has revealed a complex shape to the boundary region. Some areas are compressed and active, while others appear diffuse and quiescent. This asymmetry suggests that external forces are influencing the heliosphere, shaping it dynamically. Intriguingly, the asymmetry doesn't align with the galactic plane or the Sun's motion, hinting at influences from sources that are not yet fully understood, possibly interstellar magnetic fields. The nature of time itself might be behaving differently in this zone, not in a science fiction sense, but in terms of how energy exchange is temporally resolved. Some data suggest that particle interactions are delayed beyond what simple travel times would indicate. Particles arrive with energy signatures that imply they should have interacted or decayed earlier in their journey. This temporal anomaly might point to unique plasma conditions in this region, possibly affecting energy transfer. On top of these puzzling phenomena, Voyager 2 has transmitted evidence of low-frequency electromagnetic oscillations within the plasma, suggesting coherence among the particles. These plasma oscillations form patterns that imply the plasma is being influenced by large-scale structures. If the interstellar medium can support such waves, it forces a reconsideration of how energy and information move through the galaxy. These coherent structures might offer insights for future spacecraft navigation. If such waves can carry energy efficiently across distances, they could potentially be studied for low-energy travel. More immediately, their discovery implies that interstellar space is structured and dynamic, challenging our previous assumptions. Perhaps most intriguing is a series of data anomalies related to temperature. Voyager 2 has recorded localized temperature shifts across stable regions. These abrupt transitions, drops, or spikes in temperature within small spatial scales may indicate undetected boundary layers or shock fronts. If so, the outer solar system hosts a complex space weather environment, potentially more dynamic than the inner solar system. This adds a new dimension to our understanding of space hazards for future missions. Alongside the scientific conundrums, Voyager 2 has stirred philosophical questions about the nature of boundaries. What does it mean to exit the solar system if the heliopause is neither fixed nor uniform? If it interacts intimately with the interstellar medium, crossing it might be more akin to entering a transitional zone than a sharp boundary. Perhaps there is no true outside, just varying degrees of connectivity between the Sun and its galactic surroundings. This could lead to a broader definition of the solar system, including layers of influence that extend beyond classical definitions. The mathematical tools required to describe this complexity are under revision. Fluid dynamics, magnetic field theory, and plasma physics are being updated to incorporate nonlinear and non-equilibrium processes. Voyager 2's data shows that older models, based on idealized assumptions, did not fully capture the richness of this frontier. New simulations must account for real-time feedback mechanisms and complex interactions, shaping the future of space travel, astrophysical research, and our understanding of star systems and planetary evolution. The idea of zones of influence is gaining traction. Regions where the interaction between stellar and galactic forces creates unique conditions. The region Voyager 2 is traversing may be one such zone. It may host chemical interactions that produce novel compounds, catalyzed by the unique mix of radiation, plasma, and interstellar dust. Organic precursors, potential building blocks of life, might form in such a space, driven by processes we can't yet replicate in laboratories. If so, the boundary of the solar system could play a role in the chemical origins of life, not Earth's biochemistry, but as a cosmic synthesis zone. Furthermore, Voyager 2's findings suggest that the boundaries between star systems are active regions of change. The solar system's movement through the galaxy involves passage through interstellar clouds and magnetic fields, each potentially reshaping conditions within the heliosphere. With the data now arriving, it's plausible that Earth has experienced cyclical exposure to such regions in the past. These cycles could leave signatures in geological records, possibly influencing climate or radiation exposure. The role of dark matter might intersect with Voyager 2's findings. While dark matter remains undetected directly, some hypotheses suggest it could influence magnetic field propagation in subtle ways. If such a structure exists in our region of the Milky Way, it might contribute to some of Voyager 2's anomalies, offering a chance to study dark matter's effects indirectly through interstellar plasma and magnetic orientation. Adding to the complexity is the idea that Voyager 2 is moving through a multi-phase environment, not just in plasma terms, but in chemical composition. Spectral analysis indicates traces of heavy elements and molecules at unexpected distances. These may be remnants of ancient supernovae, carried by galactic winds over millions of years. Their presence suggests the outer solar system has been enriched by distant stellar events, infusing it with byproducts of long-extinct stars. This adds a poetic resonance to the discovery. Voyager, a machine built by humans from stardust, is now traversing the remnants of cosmic explosions that predate our Sun. There is a profound symmetry in this voyage. Launched during the Cold War, equipped with analog technology and a golden record bearing greetings from Earth, Voyager 2 was not expected to deliver such significant revelations this late in its life. Its endurance and the clarity of its discoveries remind us that the quest for knowledge does not require cutting-edge technology to be impactful. The spacecraft is old, but the questions it raises are timeless. Questions about the nature of the universe, the meaning of borders, the interaction of chaos and order, and the beauty of the unknown. Voyager 2's journey through this remarkable region is not just a technical achievement, it's a moment of discovery for planetary science, cosmology, and human thought. The space it travels is layered with invisible dynamics and cosmic secrets that expand the language of space physics. With each data packet received across the vast distance, Voyager 2 becomes a narrator of a story that challenges expectations, a tale of complexity, discovery, and cosmic wonder at the threshold of our solar system. And still, it moves. Still, it sends. Every transmission from Voyager 2 is a spark from a machine older than most people alive, yet more relevant now than ever. It invites us to reconsider what we thought we knew, to question the boundaries we drew, to consider that beyond every edge is not an ending, but another beginning. Voyager 2's venture into the enigmatic frontier between the solar system and interstellar space has become a detailed chronicle of an uncharted zone that challenges the foundations of astrophysics. As it drifts further from the Sun, it gathers data that defy predictions, demanding updates to established paradigms. One of the most novel revelations is the detection of shockwave echoes, delayed ripples in particle density, and magnetic field disturbances that appear to be remnants of older solar events. These echoes have traveled immense distances, interacting with the interstellar medium and reaching Voyager 2 years after their originating solar flares or coronal mass ejections occurred. This suggests that interstellar space may act as a resonant medium, capable of storing and reshaping energetic waves. Unlike the heliosheath, the turbulent area just inside the heliopause where solar wind slows and interacts with the interstellar medium, this outer region exhibits a combination of stability and activity. There are signs of large plasma structures that remain consistent over time, even while energetic particles exhibit dynamic behavior within them. These structures, invisible to the eye, influence magnetic field lines, creating complex patterns. Such features have not been observed in controlled environments and suggest an electromagnetic architecture beyond the planetary realm. Equally notable is the evidence suggesting that the outer solar system is laced with particle flows that resemble patterns in Earth's atmosphere. These aren't merely directional flows of high-energy particles. They form dynamic paths that vary over time. Unlike solar winds, driven directly by the Sun, these interstellar flows may be influenced by larger galactic-scale forces. What Voyager 2 has encountered is not empty space, but a dynamic system of currents and interactions, with distinct flow regimes and boundaries, all invisible until now. One of the more surprising chemical signatures Voyager 2 has reported is the detection of unexpected ion species. It has found higher than expected concentrations of negatively charged oxygen ions and traces of iron and nickel nuclei at energies suggesting a non-local origin. These ions are not thought to have been generated by the Sun or nearby supernovae. Instead, their presence points toward diffusion from distant events, possibly ancient stellar cataclysms. The implication is that interstellar space is a chemical environment where the building blocks of future planetary systems mix over long timescales. In tandem with the exotic ions, the probe has also encountered dust grains that differ significantly in structure and size distribution from those found within the heliosphere. These grains are smaller, more irregular, and coated with layers of unknown origin, possibly organic compounds or frozen volatiles. As the dust interacts with the magnetic and plasma environment Voyager 2 is mapping, it charges up and behaves dynamically, occasionally triggering secondary emissions detected by the spacecraft's instruments. These interactions open a new field of study in dust-plasma interactions, a critical process in galactic evolution. Equally groundbreaking is the discovery of what appear to be field discontinuities, abrupt changes in magnetic field orientation over small distances. These appear to form structured interfaces in space. Their formation mechanism is unknown, but they may be related to plasma interactions or large-scale currents. These discontinuities could influence particle acceleration, potentially explaining why certain cosmic rays gain energy without an apparent source. Delving deeper into the energetics of this zone, Voyager 2 has recorded a type of turbulence distinct from the plasma interactions familiar from heliospheric studies. This turbulence has characteristics where energy moves preferentially along one dimension, forming regions of intense activity interspersed with calmer areas. This structured turbulence may be common in magnetized astrophysical environments, but had not been confirmed through direct measurement until now. The implications suggest that energy transport in space may occur in complex patterns, challenging how astrophysicists model diffusion and energy dissipation across cosmic distances. Moreover, Voyager 2 has provided evidence that pressure disturbances moving through plasma can persist in interstellar space, resembling wave-like patterns. These disturbances carry information about the medium they traverse. Their existence transforms our understanding of space as a dynamic medium, capable of supporting complex interactions. Another curious signal Voyager 2 has picked up involves the detection of low-frequency radio emissions with distinct polarization characteristics. These signals, while faint, are ordered and repeat at intervals that suggest a connection to external events. They may be tied to galactic-scale magnetic oscillations or interactions with distant astrophysical sources. If confirmed, they could offer a method for studying the galaxy's magnetic structure. Even as these discoveries unfold, Voyager 2's instruments continue to detect interactions that suggest new areas of physics. One such area involves subtle interactions between electromagnetic and gravitational influences. These manifest as small deflections in high-energy particle paths that cannot be fully explained by known sources. If real, this effect could point to complex interactions in high-energy